Good day, fellow learners. Welcome to today's technical science lesson. My name is Lepan and my surname is Kelly. This lesson is brought to you by the Department of Education in collaboration with the Discovery Center. So now for today's knowledge area, we'll be focusing on electricity and magnetism. And for today's topic, we'll be focusing on electromagnetism, which is part of the examination day. Now, the application for paper 1 is that you will have your section A, which consists of 10 multiple choice questions.
And ask yourself.
Good day, fellow learners. Welcome to today's technical science lesson. My name is Lepan and my surname is Kelly. This lesson is brought to you by the Department of Education in collaboration with the Discovery Center. So now for today's knowledge area, we'll be focusing on electricity and magnetism. And for today's topic, we'll be focusing on electromagnetism, which is part of your paper 1 there for the examination. And the mark allocation for paper 1 is that we have your 10 multiple choice questions. So that is under your section A, which consists of a total of 20 marks. Then we have under section A, either 8 matching items or one-word items, which consists of a total of 8 marks. Then we have your section B, which consists of structured or long questions and has a total of 122 marks. And the total for paper 1 is therefore 150 marks with a duration of 3 hours there. Okay, now the topics to be covered in paper 1 will be your mechanics, which consists of 93 marks and a percentage weighting of 62. And then we have your electricity and magnetism, which consists of 33 marks and a percentage weighting of 22. Then we have your wave, sound, and light, which consists of 24 marks and a percentage weighting of 16. Okay, so now when it comes to electromagnetism and the examination guideline, so this is what we need to cover. So it says a current carrying conductor produces what? A magnetic field around it. Bullet number 2 says we need to determine the direction of the magnetic field that is around the current carrying conductor using the right-hand rule. Then it says you need to draw the magnetic field lines that is around a straight current carrying wire or a conductor. And then current carrying loop of a single wire. Then we need to be able to define what? We need to be able to define electromagnetic induction. So remember we said that when it comes to the definitions that we are going to define according to the examination guidelines. Again, we need to be able to define what? Your magnetic flux. And we also need to be able to give what? We also need to be able to give the units there. Then we need to be able to use the equation that is to calculate the magnetic flux density, and the what? And the area of a loop. Then it says we need to be able to define what? The magnetic flux density, state what? Faraday's law. And then also note the negative sign when it comes to your calculation of the EMF there. Then lastly, we need to know what? We need to know generators and what? Generators and the motors there. Okay. So it says here, an electric current that flows in a conductor. So we have an electric current that is going to be flowing in a conductor Okay, so with the word conductor, we mean what? Electric current that is going to be flowing in a wire. It says that current that is flowing in a wire. So if we have a current here flowing in a wire that is a conductor, it says that it has a number of effects. Number one here says that this electric current will cause heating, and it says the friction caused by the current causes the conductor to do what? Causes the conductor to heat up. So we are therefore saying that when current is flowing in the conductor, we are going to be having friction that is caused by what? That is caused by the current. And when we have that friction caused by the current, we are therefore going to have what? The conductor will therefore heat up. Okay? Then it says the greater the current, the more the heat that is what? That is generated. Number two, an electric current, what does it do? It says that we are going to have a magnetic effect. Then it says a magnetic field is therefore generated around any conductor. So these lines here would therefore be representing what? Would therefore be representing a magnetic field that is produced where it says around a conductor. So it means that we now have these lines which are called the magnetic field. They are produced around what? So this line here, it represents a conductor, and then it says when an electric current is flowing through it. Okay, so we are saying that in a conductor, we have what? In a conductor, when the current is flowing, the current will cause what? It is going to cause these lines here, which represents what? Which represents a magnetic field. Okay. Then it says here, a magnetic field is generated around any conductor. Remember, by the word conductor, it means what? It means a wire. Okay, so a magnetic field is generated around any conductor when an electric current is flowing through it. Okay, so we are therefore saying that we are going to have a magnetic field when what is happening? When current is flowing. Where is this current going to be flowing? It's going to be flowing in a conductor. Okay, then it says here, we have a wire with current that is coming towards you. So if this one here represents what? If the circle there with the dot, it represents a wire, we will therefore say that the dot inside the circle, so the dot inside the circle, what does it represent? We are therefore saying that it represents the current that is coming towards you. So when we want to represent a current coming towards you, we are therefore going to use what? We are therefore going to use a dot. And then on the right, it says that wire with the current going away, wire with the current going away from you. So when we want to represent the current that is going away from you, we are going to use what? We are going to use a cross there. Okay. So when it comes to the right-hand rule, we are therefore saying that it says the pencil points in the direction of the what? The pencil is going to point in the direction of the current flow. So if you look at the tip or at the top of a pencil, the writing side, you are going to see that at the top of the pencil, that is where you have the what? That is where you have the dot. So it therefore means that if you want to use the right-hand rule, then you will have to hold what? The pencil in this case, it represents a conductor. Remember, a conductor is a what? A conductor is a wire. So if we want to represent the current that is coming towards you, it therefore means that the tip or the top of the pencil is going to represent the current that is coming with, the current that is coming towards you. Okay, then it says the fingers curl around in the direction of the what? In the direction of the field lines. So if the pencil is a conductor or a wire, we are saying that this thumb is going to represent what? The thumb is going to represent the direction of the current. And then we are saying that at the top, we are going to represent the current that is going to come towards you. And then if you look now at the back of the pencil, the back of the pencil will therefore be represented by what? It will be represented by a cross. So when you look at a cross, we are saying that the current is going where? The current is going away from you. And then now the fingers now around the conductor or the wire. So they would be representing these lines here. And these lines are therefore the what? Are therefore the magnetic field lines. So as you look at the magnetic field lines and their arrows here, we are saying that the magnetic field lines are going to go in which direction? Because the arrows are facing to the left-hand side, so therefore the magnetic field lines are going to go anti-clockwise. But if the current is going what? Is going away from you. Remember we said that we are going to use what? We are going to be using a cross. So if the current is going away from you using the right-hand rule, therefore, because the arrows now are facing to the right, if you think of a clock now, it's going to be going in which direction? Because it's going to the right, the arrows are going to the right, therefore the direction will be clockwise. But if the current is coming towards you, the direction of the magnetic field lines is therefore going where? Anti-clockwise, okay? Then with the right-hand rule again, or the grip rule, it says that the thumb, we said the thumb is what? It will represent the direction of the conventional current. So now remember, with conventional current, we said that conventional current is going to flow from where? Conventional current flows from the positive terminal to the negative terminal. So this one here, it represents what? It represents the conductor or the wire. And then the thumb here represents what? The direction of the conventional current. And then the fingers. So the rest of the fingers then are going to represent the magnetic field that would be there around the magnetic field that would be there on the conductor there. So because we said if the arrow now are moving to the left like that, it therefore means that it's moving where the magnetic field is going to go in an anti-clockwise direction. Now we can also have what we call a solenoid. So a solenoid, it says wires coiled into circular turns. So that is now us having a lot of wires that are then curled into circular turns, and then it says these wires. So this is an example of a solenoid as well as that, okay? So now it says these wires are then connected to a what? To a potential difference. So they would be connected to a potential difference. For example, a what? For example, a battery there. Then it says magnetic field is produced, okay? So we said that when we have current that is flowing in a conductor, what is going to happen? We are saying that a magnetic field will be produced, okay? And now this magnetic field that is produced will be produced where? In the interior and the exterior of the solenoid. So we can see that we have, so inside the solenoid, we have magnetic field lines that are produced. And outside of the solenoid, we also have what? We also have magnetic field lines that are produced. Hence, we are saying that a magnetic field will be produced where? In the what? In the interior, that is in the inside of the coil, as well as what? As well as outside there. Then we have a right-hand rule with the solenoid as well, okay? So with the right-hand rule, again, this is a representation of what? That is a representation of the solenoid, okay? With the right-hand rule, we are saying that we are going to use what? We are going to use the fingers to represent what? To represent the direction of the conventional current. So the fingers this time, they are now representing the direction of the conventional current. And then we have the what? We have the thumb. The thumb then is going to represent what? It's going to represent the direction of the what? Of the magnetic field. And with the magnetic field, we are saying that they are going to be moving from where? They are going to be moving from the South Pole to the North Pole, or from the South Pole to the North Pole, and that is inside of the coil. So we are therefore saying that inside the coil, the magnetic field lines are going to be moving from the right-hand side, which is the South Pole, to the left-hand side, which is the North Pole, inside the coil. But outside of the coil, we can see that what is happening now, the magnetic field lines are moving from what? They are going to be moving from the North Pole to the what? To the South Pole. So North Pole to the South Pole there. Okay. So learners, if you have any questions, you can send your questions to the following WhatsApp number, 079-578-2908 there. If you have any questions, you can send your questions to the following WhatsApp number, 079-578-2908. Okay. So just to summarize again, we said that we have a straight conductor. So a straight conductor would be a wire that is not curled. So which is this one here. And then we also have what? We also have a solenoid. So with a solenoid would be a wire that is now curled. So with the right-hand rule, we are saying that you are going to be using your thumb, that is to indicate what? The direction of the conventional current. And we said that conventional current is going to flow from the positive terminal to the negative terminal, okay? And then we said that the fingers are going to represent what? The fingers are going to be representing the direction of the magnetic field lines there, okay? So, and then again, we also said that if the current is going to go into, or the current is going to be pointing towards you, we said that we are going to be using what? We are going to be using a dot. Remember when we used the pencil example, and then if the current is pointing where? Is pointing away from you, therefore we are going to be using what? We are going to be using a cross, okay? So now with the solenoid, okay, with the solenoid, we are therefore saying that the thumb is going to represent what? Is going to represent the direction of the magnetic field. And then we said that the magnetic field inside the solenoid is going to flow from where? It's going to flow from the South Pole to the North Pole. That is inside where? Inside a coil. But outside of the coil, we said what? We said that the magnetic field lines are going to be moving from the North Pole to the South Pole, okay? So the thumb is indicating what? The direction of the magnetic field lines, and then the fingers are therefore representing the what? The fingers are therefore representing the direction of the conventional current there. So now we have electromagnetic induction. So according to the examination guideline now, it says we need to define electromagnetic induction as the production of what? Production of an electromotive force, or EMF, or the voltage across an electrical conductor, and that is due to the relative motion between the conductor and the magnetic field, or the process of what? The process of generating electricity from what? From motion. So with electromagnetic induction, we are therefore saying that we are going to induce. To induce means to produce what? A voltage or a current. And how are we going to produce or induce that current? We are going to produce that current. It says that is due to the relative motion between the what? Between the conductor. So by the relative motion between the wire and the magnetic field lines, okay? So then it says changing the flux linkage between a conductor and a magnetic field. And then it says an EMF or potential difference is what is induced. So it's basically the same thing to say that as we change the flux linkage, or the number of magnetic field lines that are going to be passing through a wire. Therefore, also changing the conductor, it says that we are going to be doing what? We are going to be inducing or producing what? Or producing an EMF or current as well. Okay, now with electromagnetic induction, it says when the speed at which the magnet is moved in and out of the coil is increased, the rate of change in the magnetic flux is also going to do what? Is also going to increase. Okay, so this one here, it's representing what? It's representing a wire. So if it's now more than one, we can therefore say that we are representing what? We are representing a coil there. So now with that coil, we have what? We have a magnet which has what? The north and the south pole. And then over here, we have a light bulb, or we can also use what? We can also use a voltmeter. So we are therefore saying that if you are to move the magnet in and out of the coil, or it says when the speed at which the magnet is moved. So when this magnet is then moved inside and outside of the coil, the rate at which electricity is produced is going to do what? The rate at which the electricity is produced is also going to increase. So therefore, using a FET simulation, then we can also say that if you are going to be moving this magnet in and out of the coil, the light is going to do what here? The light is going to light up. But you will observe that if the magnet is not moving, therefore the light will not do what? The light will not be having a reading. As well as if we are to replace the light bulb and use a voltmeter, you will observe that if you move the magnet in and out of the coil, you will observe that you will have a reading, whether it's a negative reading or a positive reading of the voltmeter. But you will observe that as you increase the speed, or as you move the what? As you move the magnet, as you move the magnet in and out of the coil, you are going to have what? You are going to have a reading. But as you then stop moving the magnet, so the very same magnet here, you will then see that you will not have what? You will not have a reading. Then it says the rate of change in magnetic flux is therefore directly proportional to the induced EMF. Okay, so the rate at which the magnetic flux, or the number of the magnetic the number of the magnetic field lines enter the coil, that will therefore increase the production of the what? It will therefore increase the production of the EMF. So we said that by the word induce, we are therefore going to do what? We are therefore going to produce electricity. So overall, what is it that you need to understand? We are therefore saying that if you move a magnet in a coil, it's going to induce, it's going to produce electricity. But if there is no movement when it comes to the coil, relative to the magnet, therefore there will be no electricity that is induced there. Then it says the induced EMF, or the extent of deflection of the needle, increases with an increase in the change of the magnetic flux. Okay, so basically the same thing, but more relating to this one. So the needle in this case, we are referring to the needle when it comes to the voltmeter. We are saying that as you move the magnet in and out of the coil, the needle will therefore begin to move. But as the magnet stops moving, therefore there will be no what? There will be no movement when it comes to the needle of the voltmeter there. Okay, then next it says define magnetic flux density as the number of what? The number of field lines per unit area measured in what? Measured in Tesla there. Okay, so measured in Tesla T. Okay, so we are therefore saying that these blue lines here, they represent what? They represent the magnetic field lines. So with the magnetic flux density, we are saying that it will be the number of the magnetic flux the number of the magnetic field lines that are going to be going in that coil there. So if the circle here represents the coil, we are saying the density or the number of the magnetic field lines that are going to be going into the coil. Then next we have, it says define magnetic flux. So that is the number of field lines that are going to be perpendicular to a given area, and they are measured in what? They are measured in Weber, which is then what? Which is then W. So with the magnetic flux, we are saying that the very same blue lines that are going to be going in a certain area, but these blue lines that are now perpendicular to a certain area. Okay, then magnetic flux, we are saying that it's measured in what? In Weber. And then we are saying that for the magnetic field strength, or also called the magnetic flux density, is measured in Tesla. And then we also have what? We also have the area. So it says area perpendicular to a certain or to a given area, to a given surface. So the area will depend on the type of coil that you are given. So if they give you a circle, then it means that you are going to calculate based on that. If they give you a square, then it means that you are going to calculate based on that as well. Then we have what? We have theta there on the formula. Theta, it says it is the angle between what? It is the angle between B and the normal to the area. So the angle between the magnetic field and the normal. So how do you draw a normal? The normal would be at a 90-degree angle to whatever surface that you have there. Then next we need to be able to define Faraday's law. So it says the EMF, which is what? Which is E induced around a single loop of conductor. So the EMF, okay, which is induced, we said what? It's to produce, is proportional to the rate of change of the magnetic flux. So the EMF is directly proportional to the change of the what? Of the magnetic flux, and that is through the area A of the loop. And then this can be stated mathematically as that there, okay? So with the formula now, we are saying that E is going to represent what? E is going to represent the EMF that is induced. And the EMF that is induced measured in what? Measured in volts there. With N, we are saying that that is going to be the number of turns or the number of coils that we have. And then with the change in phi, we are going to represent what? Change in the magnetic flux, and it's measured in Weber. Now we have the change in time. The change in time would be the time taken. Then it says, note that the negative sign indicates that the EMF, so we are speaking about this negative sign, it says that it indicates that the EMF is in the opposite direction to the effect that it produces there. Then it says Faraday's law relates induced EMF to the rate of change of the magnetic flux, which is the product of the magnetic field strength and the cross-sectional area the field lines passes through. So basically, again, we are saying that with Faraday's law, we are going to relate what? We are going to relate the EMF that is produced, and we are going to relate it to the change of the magnetic flux, okay? And then it says the cross-sectional area changes as the loop of the conductor rotates, which gives rise to the cos theta factor. So this one here would be representing the magnetic field lines, and that would then be representing your coil. So with the coil, then it will therefore mean that you will need to, or you will be able to calculate your what? You will be able to calculate your area. And then this one here would be representing your normal. Your normal is therefore perpendicular to what? Is therefore perpendicular to the given surface area. So in this case, the given surface area is based on what? It's based on a rectangle there. Now it says, according to Faraday's law, the magnitude of the induced EMF or the potential difference, it depends on the following. So we have N according to the formula, and then N says it's the number of turns on the coil. So by the number of turns, if we look at the diagram here, so we have what? On this diagram, we have what? We have one coil. So, and on this one, we have how many? We can see that we have 3 coils. So if we increase the number of coils, if we increase the number of turns on the coil, it says what? We are going to have more turns, so we are going to have more coils. When we have more coils, what are we saying? We are going to induce, or we are going to produce a larger EMF. So we can also observe that on the first picture here, the light bulb is not as bright as the light bulb on the right-hand side. So why is that? It's because the light bulb on the left-hand side has how many turns? It has 1, or it has, it has 1. And then the light bulb on the right-hand side has how many coils? It has 3 coils. So then if we increase the number of coils, therefore, we are saying that we are going to produce what? A larger EMF. Then according to the formula, we have what? We have the change in time. So we are therefore saying that the change in time is therefore inversely proportional to the EMF. But with the number of turns is directly proportional to the EMF. So if for the change in time, it says that the rate at which the coil is turned. Okay, so if we are, it's either we are going to be turning the coil, or in this case, if you use a FET simulation, you will see that we are turning the what? We are turning the magnet. So it says the rate at which the coil is turned, it means that we are going to have what? It means that we are going to have a greater relative speed. Now, when we have a greater, or when we have a greater speed, it therefore means that we are going to be producing what? We are going to be producing a larger EMF there. Then next we have change in phi, which says the change in the strength of the magnetic field. So it says as the magnet is brought nearer. So this one, it represents what? It represents the strength of the magnet. Then it says the current increases due to an increase in the strength of the magnet. Okay. So it therefore means that change in phi is what? Change in phi is directly proportional to the EMF, and that is according to our formula. So you will see that if you are to use what? If you are to use a FET simulation, you will see that this one here, it represents the what? It's representing the current strength, or the change in phi. Okay, so you will see that if the strength is at this bar here, or it's in between 0 to 50%, you will observe that the light does not is not as bright as the light that is observed where that is observed on the right hand side. So with the one that is on the right hand side, you will then see that if you then increase what? If you then increase the strength of the magnet, therefore the light will do what? The light will become what? It will become brighter. So hence we are saying that if we increase what? If we increase the strength of the magnet, which is the same as the change in phi, therefore the EMF induced, so the electricity that is produced, would therefore also do what? Would therefore also increase there. Then it says here the induced EMF is directly proportional to the rate of change of the magnetic flux linkage. Okay, so we are speaking about the EMF and the what? And the change in the magnetic flux linkage there. So we are therefore saying that the two are what? The two are directly proportional. Remember we said that the EMF is also directly proportional to the number of turns. As we said that if we increase the number of turns, what will happen? If we increase the number of turns, then the EMF induced will also be larger. But then we said that the EMF is inversely proportional to what? To the change in time. Okay. Then it says here the induced EMF can be increased by the following. Remember we said what? Number one, if we increase the number of coils. Number two, we are saying that if you use what? If we use what? A stronger magnet. So if the number of coils, we were referring to these ones here. And then number three, if we do what? If we decrease the time. So if we decrease the time, then what is going to happen? the magnet or the coil is going to do what? The magnet or the coil is going to be moving faster there. Okay, then we have the basic principle of an AC generator. So it says the principle of rotating a conductor in a magnetic field to generate current is used in what? Is used in electrical conductors. Then it says a generator converts what? Converts mechanical energy, that is motion, into electrical energy. Okay, and with the definition, it therefore says that a generator is so our keyword there is what? It is a device that will do what? That converts what? That converts mechanical energy into electrical energy. So with mechanical energy, we are saying with generators, we are converting what? We are converting motion into electrical energy. So remember, again, with the definitions, you need to define according to the examination guidelines there. Okay, so Lennox, I'm going to ask that we take a 2 minutes break there. Okay, welcome back, learners. So if you have any questions, you can send your questions to the following WhatsApp number, 079-578-2908. So if you have any questions, you can send your questions to the following WhatsApp number, 079-578-2908 there. So it says the basic principle, so that is what we need to know. The basic principle in terms of generators, it's what? It's your electromagnetic induction. And it says a conductor moves in a magnetic field. A current is what? A current is induced, okay? So we are saying that if a wire, so a conductor, a wire is moving in a magnetic field, so moving in that magnetic field lines, therefore we are saying that what is going to happen? A current will be induced. The word induced is what? Will be produced. Remember we said that when we had the current produced, we had what? The light was getting what? The light was getting brighter there. Or we said that when we're moving the magnet there inside the coil, we were producing what? We were producing the light there. So then it says here, force applied to move a conductor. So when the force is applied to move a conductor, it's going to cause a change in the what? It's going to cause a change in the magnetic field. And then when that happens, we are going to induce current. Inducing current means what? We are going to be producing electricity. Then it says a generator consists of a coil that is connected to what? a coil that is connected to an external circuit. So with the coil again, we are saying that it's the same as what? It's the same as a conductor or a wire. Then it says the coil is therefore rotated. Where is it rotated? It's rotated inside the magnetic field there. Then we have two types of generators, okay? So we have a direct current generator. So by the word direct, we mean what? A DC. And we also have what? An alternating current generator. So by the word alternating, we are simply saying what? AC, and direct current, we are simply saying what? It's your DC. Generators operate based on the principle of what? On the principle of Faraday's law of what? Of electromagnetic induction. So remember in the exam, they can ask you what do generators, or what is the principle that generators work on. Then you would have to say what? Faraday's law of electromagnetic induction. Then you can also be asked, it says, the energy conversion that takes place in a generator is what? Mechanical energy to electrical energy, okay? So this is then a diagram of a what? This is then a diagram of a generator. Then we have what? When it comes to the components of a generator, we have an armature. An armature in this case is the coil there. Then we have what we call what? We have what we call the slip rings. But when it comes to the slip rings, you will then see that we have how many in terms of the generator? We have two. And then we also have the carbon brushes there. The carbon brushes. And then it says that we have what? Two poles of the magnet or permanent magnets. So we have what? We have the North Pole as well as the South Pole. And then these lines here are just a representation of the what? Are just a representation of the magnetic field lines. So magnetic field lines are going to be moving from where? Are going to be moving from the North Pole all the way to the South Pole there. Then we have a DC generator. With a DC generator, again, what is it that we have? We have the coil there. But with a DC generator, you will see that, remember with an AC generator, we had what? With an AC generator, we had slip rings. But with a DC generator, we then have split ring what? Split ring commutator. And then again, we have what? We have the carbon brushes, which are then connected to your split ring commutator. But with your split ring commutator, you will see that it's divided into what? Into two halves there. Then again, we have what? We have the two magnets, and with those two magnets, we have the magnetic field lines. And then again, we are saying that the magnetic field lines, where are they going to be moving from? The magnetic field lines are going to be moving from the North Pole to the South Pole there, okay? So now comparison of a DC and an AC generator. Okay, so when it comes to the principles, both of them, they work on the principle of what? Of electromagnetic induction. And then when it comes to the energy conversion, both of them are converting what? Are converting mechanical energy to electrical energy. But then when it comes to the rings that are there, with a DC generator, we are therefore saying that we have what? We have split rings. But with an AC generator, we have what? We have your slip rings. And then again, you need to know some examples or uses of a DC generator or an AC generator. With a DC generator, it says it is used for what? It is used for electroplating with metals. So that chapter, you will then find it where when it comes to your electrochemistry there. And then it says electrolysis for the manufacture of what? Of chlorine, refining of aluminium, copper, and manganese. And then it says many DC generators are driven by what? By your AC motors. Okay, other examples, then we have examples of what? Of your AC generator. It says electricity generation at power stations, generators at amusement parks, hospitals and other essential services. And then it says building sites, lights at accident scenes as well. Okay. Then we have the EMF graph, or the induced EMF, or the voltage. So we can also talk about what? We can also talk about the voltage as well as what? As well as the current that is produced. Okay. So we are therefore saying that with this one, this represents what? This represents the magnet. And we are saying that as the magnet is rotated between what? Between the North Pole and the South Pole, we are going to be having magnetic field lines. And those magnetic field lines are going to be running from what? Are going to be running from the North Pole to the South Pole. So we are therefore saying that as the magnet is rotating, we are going to be producing maximum current or zero current or zero voltage. So we can relate voltage with what? With the current. Okay. So if now the magnet and the magnetic field lines are what? If the magnet and the magnetic field lines are parallel to each other, we are therefore saying that the angle between the two is then what? The angle between the two is 0. So if the angle between the two is 0, it therefore means that we are going to have cos theta according to our formula. And when we have cos theta, we are therefore saying that we are going to be inducing what? We are therefore going to be inducing zero current or zero voltage. But if the magnetic field lines and the coil are what? And the coil are at a 90-degree angle to each other, therefore we are going to be having what? We are going to be having cos theta. And when we have cos theta, we are going to be producing maximum current. So again, here we are saying that the coil and the magnetic field lines, if they are parallel to each other, we are not going to be inducing any current or any voltage. And then when the magnetic field line and the coil are at a 90-degree angle to each other, we are going to be inducing what? Maximum current. And then again at 360 degrees again, if the coil and the magnetic field lines are what? Are parallel to each other, we are going to be inducing what? We are going to be inducing a zero current there. Then we have what? Motors. It says the electric motors operate based on the motor effect there. Now with the motor effect, it says a current carrying conductor in a magnetic field produces what? It produces a turning effect, and that is due to a force that is acting on the conductor. And then now with what we need to know again when it comes to motors is that they are now going to convert what? They are now going to convert electrical energy to mechanical energy, as compared to generators that were converting mechanical energy to electrical energy. And then again with motors, we have two types. We have a DC motor as well as an AC motor there. And then when it comes to the generator, then we need to know that we need to use what? We need to use the right-hand rule, okay? And then with the right-hand rule, we are saying that the thumb shows the direction of what? The thumb is going to show the direction of motion, okay? So that would be you now showing the direction of motion of the coil. So if you are to push the coil there, that would therefore represent the direction of motion. So if you are to push the coil upwards with your thumb, it therefore means that it's going to move in which direction? It's going to be moving in an anti-clockwise direction. So that is the thumb is the motion or is the force that you are going to be applying. And then we have what? We have the first or the index finger, this one here. The index finger is going to represent what? The direction of the magnetic field lines. The direction of the magnetic field lines, how are we going to determine it? It's going to be moving from the north to the south pole there. Okay, so that would be now your first finger indicating that the direction of the magnetic field lines is from the north to the south. Then this one here, it says the second or the middle finger, it shows what? It shows the direction of the induced EMF or the induced current. Okay, so the produced current or the produced what? The produced voltage in this case. So you need to make sure that you know how to use what? How to use the right hand rule. So we are saying that with the thumb, you are pushing, you are applying the force, so that is F. Then with the second finger, you are going to show what? The direction of the magnetic field lines. So the direction is going to be from the north to the south. And then this finger here is therefore going to, or the middle finger is therefore going to show what? The direction of the conventional current there. Then we have a motor effect. It says this phenomenon that a current carrying conductor in a magnetic field will experience a force causing it to move is therefore called what? Is therefore called a motor effect. And then it says the strength of the force increases when what? The current in the conductor is increasing, so therefore the strength will increase when we use what? When we use a stronger magnet. Okay, and then when what? When the number of turns do what? When the number of turns also increase. Then it says the force experienced are strongest when the conductor lies what? When the conductor is going to lie what? Perpendicular to the magnetic field lines there. So for a motor, so these are the components that we have. We have a coil. So we said that a coil means a coil is a conductor, or a coil is a wire, or we can also call it what? We can also call it an armature. And it says it cuts through the magnetic field and it produces what? And it produces rotation. So we have this coil here, and this coil is cutting through the magnetic field. And that then produces what? And then it produces rotation. Then we have what? We have your carbon brushes. And then the carbon brushes, it says it allows the current that is produced to be transferred from the what? So it will allow the current that is produced and that is to be transferred to the what? To be transferred to the external circuit then. Then next we have what? We have a power supply. And this power supply, it then supplies what? It then supplies the electrical energy. So now with this one, we have what? We have a split ring what? A split ring commutator. So remember, when it's slip rings, we are going to have how many of them? It's going to be 2 of them. And with a split ring, the ring will be split into 2 and it's going to be 1 ring there. Then a split ring commutator, it says, allows the current to flow in what? It allows the current to be flowing in one direction, so that the armature rotates in what? In one direction, so that this wire is able to rotate in the very same direction. But it therefore means that with a slip ring, therefore we are going to have what? We are going to have the current that is not flowing in what? In one direction there. So for a motor, we have the left-hand rule. For the left-hand rule, if you have what? If again you have a coil there, it says that the thumb shows the direction of the applied force or the motion. So this would now be the thumb there representing the direction of the force. So again, if you are to push the coil upwards using your thumb, then the coil would be turning in which direction? Then the coil would be turning in a clockwise direction. But now what we also need to know is that we are going to be measuring the what? The magnetic field lines, they need to be flowing from the north pole to the south pole. So you're going to use your left hand, then the thumb is the force, and then the first finger, it says the first finger, it says it shows the direction of the what? Of the magnetic field lines, okay? And then the second finger, it says that it will show you the direction of the current. So again, if you are to push the wire up, if you push the wire up and you are going to point the first finger where from the north to the south pole, this finger here would therefore indicate the direction of the current. So it therefore means that the current will be flowing where? Will be flowing towards you in this case. Then we have a DC motor. So with a DC motor, it says that we have what? We have an armature. So an armature in this case, what does it represent? It represents the wire or the coil. And then with a DC motor, we are going to have what? We are going to have a split ring what? A split ring commutator. Then next, we are going to be having what? We are going to be having the carbon brushes there. And then it says that we are going to be having 2 poles of the magnet or 2 permanent magnets. So again, with the DC motor, we are going to be applying the very same to say that the magnetic field lines are going to be moving from where? They are going to be moving from the north pole to the south pole there. So it says here a split ring commutator in a DC motor, it reverses the direction of the current in the coil every half revolution, thus enabling the coil to continue to rotate what? To rotate in the very same direction there. Then next we have what? We have an AC motor. So now what is the difference now? With an AC motor, we will see that we have what? We have the slip rings instead of the split rings. So it says the components, we are going to have what? We are going to have an armature. We are saying that an armature is a coil or a conductor. But instead of the split ring, we are therefore going to have what? We are therefore going to be having slip rings. Then we have what? We have the carbon brushes, as well as the what? As well as the 2 poles of magnet. So the north pole and the south pole. So what you need to do for the examination, you need to make sure that you know how to label all the components of the AC and a DC motor, as well as for the generators there. Then it says the application or the uses of what? Of motors. So we can use motors, examples of motors would be your washing machines, would be your mixers, would be your dentist drill, as well as what? As well as the electric fans there. And now we have the difference between the generators and the motors. So with generators, we are saying that we are going to be converting mechanical energy to what? Mechanical energy to electrical energy. So we are going to be converting motion into what? Into electricity. But with a motor, we are saying that we are going to be converting electrical energy, so electricity to motion. So electrical energy to mechanical energy then. And then with generators, it says that it uses the principle of electromagnetic induction. But for motors, we are going to be using what? The motor effect. And for generators, what are we doing? We are producing what? Because we are converting mechanical energy to electrical energy, it therefore means that we are producing current. But with the motor, because we are converting electrical energy to mechanical energy, it therefore means that we are using the current. Now for the generators, we are going to be using what? We are going to be using the right-hand rule. And for the motors, we are going to be using the left-hand rule. So you need to make sure that for the examination, you do know all of these that we have here on the table here. And then again, when it comes to the formula sheet, make sure that you know how to use these formulas here. So your EMF and these ones for your transformers there. Okay. So learners, I'm going to ask that we take a 3 minutes break. Welcome back, learners. So if you have any questions, you can send your questions to the following WhatsApp number, 079-578-2908. If you have any questions, you can send your questions to the following WhatsApp number, 079-578-2908 there. So it says here, study the diagram of an electric motor. So they're already telling us that it is a motor because we know that we have motors as well as what? As well as the generators. And then it says, and answer the questions that what? And answer the questions that follow. Okay. So we can see that we have what? We have two magnets. We also have the coil there. We also have a power source. We have the brushes as well as the rings there. Then 10.1.1 says, what type of energy conversion takes place in a motor? Okay, so the energy conversion is there for what? Remember, we said that we are using what? Electricity, and that is to produce what? That is to produce motion. So therefore, the energy would be from, would be electrical energy to what? To mechanical energy. And then it says, is this an AC or a DC motor? So remember we said that with an AC motor, we are going to have what? We are going to have slip rings. But with a DC motor, what is it that we are going to have? We are going to have a split ring commutator. And then we said, how are we going to identify the split ring commutator? the split ring commutator it's therefore going to be two rings that are not connected to each other. So it therefore means that this would then be representing what? This would be representing a DC motor then. Then it says that we need to label the parts 1, 2, and what? 1, 2, and 3. So we can see that 1, where is 1 pointing? So 1 is pointing there by the south. So with that south, we know that that is the what? That is the magnet, because we can see that we have the north, we have the magnet which has the north pole as well as the south pole. So that would be our magnet. And then for number 2, it would therefore represent the what? It would therefore be representing the carbon brushes there. Then for number 3, what is it that we have? Remember, we said that we have this ring here. But this ring, we are going to call it what? Because now the ring is split into 2, it's not going to be a slip ring, but therefore it's going to be a split ring commutator. Okay, so we have what? Number 1, we said it's going to be the magnet. Number 2, it would be the carbon brushes that are then connected to the split ring commutator as well as to the external circuit. And then number 3, we said that it's going to be the split ring what? The split ring commutator. Then it says here, give a reason for your answer, and that is in question what? Okay, so it says here 8.3, a simplified diagram of an electric motor is what is given below. Then it says, is this motor an AC or a DC? Okay, so again, because we can see that we have what? We have a split ring commutator there. Therefore, that would be representing what? A DC. Then it says, give a reason for your answer. We said what? The split ring commutator ensures that the current is going to be flowing what? The current is going to be flowing in one direction. But if we had 2 rings there that are then connected to each other, that don't have a space there, it would therefore mean that that would now be an AC motor. But because we have a split ring, it therefore means that it's representing what? It's representing a DC motor. And then state the energy conversion that occurs in a motor. So the energy conversion, again, it would be electrical energy to mechanical energy then. Okay. Then it says in the diagram below, the coil consists of what? The coil consists of 12 turns. Okay. So remember, we spoke about what? We spoke about the number of turns. Okay. Then it says the magnetic flux then changes from what? The magnetic flux is then changing from 0.8 Tesla to 0.5 Tesla. And that is in what? That is in 2 seconds there. 10.1.1 says that we need to state Faraday's law of electromagnetic induction in what? Electromagnetic induction in words there. So again, remember with the definitions, we are going to be defining according to the examination guidelines. So it says here, the magnitude of the induced EMF is directly proportional to the rate of change in the magnetic flux there. So we said that the rate of change in the magnetic flux is what? This definition means that the rate of change in the magnetic flux is directly proportional. So meaning that if we increase the rate of change of the magnetic flux, the EMF induced or the EMF that is produced will therefore do what? Will therefore increase there. Okay. Then it says here that we need to calculate the magnitude of the what? The magnitude of the induced EMF. So which formula are we then going to use there? So for the magnitude of the induced EMF, we are therefore going to refer to the formula sheet there. And also look at what is it that we are given there. So it said that we are given the number of turns there, and the number of turns is what? The number of turns, we have how many? We have 12 there. And remember, the formula comes with what? The formula comes with a negative. So when we do the calculations, you need to make sure that you also include the negative sign. So n represents the number of turns. And then we have what? It says that we have the magnetic flux changes from. So it would be the magnetic flux final. So as it says, it changes from what? It changes from 0.82 to 0.5 Tesla. So magnetic flux final minus magnetic flux initial divided by what? Divided by the total time there. So from there, we would then multiply whatever that we have at the top and divided by what? Divided by 2 there. So as we can see that the question is out of how many marks? The question is out of 3 marks there. So that means that we will then get what? 1 mark for the formula, 1 mark for the substitution, and then 1 mark for the correct answer. And that correct answer needs to also have what? It also needs to have the correct SI unit. So, but because we said that we are calculating the what? Because we said that we are calculating the induced EMF. Induced EMF, the unit is what? The unit is volts then. Then it says, name one method which can be used to increase the what? To increase the induced EMF. So what is one method that we can use that is to increase the electricity that is produced or to increase the current that is produced? Remember we spoke of what? We spoke of increasing the what? Increasing the number of turns using what? Using a stronger magnet. So this is what we have here. It says that you can do what? You can use what? You can use a stronger magnet. So that is according to the formula here. So inducing EMF means what? Increasing the strength of the magnet. If you increase the strength of the magnet, the induced EMF will also do what? The induced EMF will also increase. Or we said you can, we said that the number of turns is also directly proportional to the number of loops. So we said that if you increase the number of turns, you are also inducing the current. Or number 3, we said that change in time is inversely proportional to the EMF that is produced there. Okay. So now for this one, learners, I'm going to ask that we take a 2 minutes break there. A 2 minutes break. Welcome back, learners. So if you have any questions, you can send your questions to the following WhatsApp number, 079-578-2908. If you have any questions, you can send your questions to the following WhatsApp number, 079-578-2908 there. 9.2 says study the diagram of a generator below and answer the questions that follow. So we now know that we are given what? We are given a generator. Then we can also see that we are given the magnetic poles, and we know that the magnetic field lines are going to be moving from the North Pole to the South Pole there. Okay. Then it says 9.2.1, identify the type of generator, write only AC or a DC generator. So with this one, again, we can see that, or we know that if we have an AC generator, what is it that we are going to observe? We are going to observe that we have the slip rings. But then if we have what? If we have a DC generator, then we will see that we have what? We have the split ring commutator. And then with the slip rings, when it comes to an AC generator, we know that it's going to be two of them, and that with a DC generator, it's going to be a split ring commutator. So with a split ring commutator, it's going to be a ring that is then cut in half then. So we therefore know that this would then be representing what? An AC generator. Okay. So again, just to remind you on this one, we said that the magnetic field lines are going to be moving from where? From the North Pole all the way to the South Pole. And we said that if the magnetic field lines are then perpendicular to the coil, it therefore means that we are going to have what? According to our formula, we are going to have what? Cos what? A cos 0. And if we have cos 0, we are therefore saying that we are going to be inducing maximum current, or we are going to be producing maximum current, okay? Or maximum what? Current or maximum voltage. And we are therefore saying that if the magnetic field lines and the coil are at a 90-degree angle to each other, we are therefore going to be having what? We are therefore going to be having cos 90 degrees. And when we have cos of 90 degrees, we are therefore saying that we are not going to be producing any current, or we can say that we are going to be producing what? Zero current there. Okay. And then again, if you are to be using your because now this is a generator, if you are going to be using a generator, we are saying that you will need to use what? You will need to use your right hand. And then we are saying that when you use your right hand, the thumb, so it means that the thumb would then be where? The thumb would then be on the left-hand side then. When the thumb is on the left-hand side, it's going to be representing the what? It's going to be representing the force. And then the second finger is going to be representing the magnetic field lines. So the magnetic field lines, they need to be flowing from the North Pole to the South Pole. And then again, we are going to have your middle finger. Your middle finger will then be representing what? Will then be representing your current there. So in this case, it therefore means that the current will be moving where? It will be moving away from you on this one, okay? Because remember, we said that with generators, which hand are we going to use? With generators, we are going to be using the right hand. And then if we had motors, then we are therefore saying that we were going to be using what? If we had motors, then we were going to be using the left hand there, okay? Then it says 9.2.2, state the function of the slip rings. So remember, we have what? We said that with the generator, we have slip rings. but with with an AC generator, we have what? We have slip rings, but with a DC generator, we have what? We have the split ring commutator. So it says slip rings, they maintain electrical contact that is between the load and the rotating coil. So between the load there and the what? And the coil there that is in between the magnetic poles there. Okay. So with that, learners, I would like to leave you with the words of Nelson Mandela, which says, "It is in your hands to create a better world for all who live in it." With that, learners, I would like to wish you all the very best for your examination, and I'll see you next time. Thank you.